So last time we took a refresher on how this restoring force, F equals negative kx, leads to a sine or cosine behavior when you plot position x versus time t. The reason for that is whenever x moves in the positive direction away from 0, this force pulls it back in the negative direction. Whenever x goes to a negative value, this force pushes it forward in the positive direction. And so it's always kind of following itself back and forth in this sinusoidal pattern. But that doesn't have to be the only force that acts on this particle, spring, whatever it is that we're looking at. You could also have some sort of damping force that works to rob the system of energy by sapping energy away into the surroundings. The simplest damping force you can have is a negative b times the velocity. And now that I've got different forces, I should probably give these labels: restoring force, damping force. Here we go. And so the idea of this one is you got a damping coefficient here. That's just a constant that tells you how dissipated the environment is. And over here you have the velocity. Now it's a velocity vector here because that indicates it's always pointing opposite of the velocity. I guess I should make that a vector too. But the important thing is this is always going to point opposite of the velocity. So when you get faster in one direction, it's going to slow you down in the opposite direction. It works a little bit different in the restoring force because the restoring force is based on where you are. The damping force is based on what direction you're traveling in. The net result is that the damping force is always going to work to rob you of kinetic energy. What that means in terms of the graph is that with a little bit of damping force, let's make that in green, this thing is not going to go quite as far each time. It's going to go a little bit less that time. It's going to go a little bit less that time, a little bit less here, a little bit less here, a little bit less here. And what you'll end up seeing is that these damping, it'll still oscillate, right? Because it still has a restoring force, but those oscillations are going to die down thanks to the damping force. Now let's suppose you want to add more energy back in. Maybe you want to add a motor to the system or something. In that case, you're looking at adding a driving force. And this driving force can really be any function of time, position, velocity. There's all sorts of interesting combinations you can try. But the sort of most basic form is to use another sine function. So you'll have some kind of amplitude. So you have some kind of driving amplitude. Excuse me, this is a force, not a position. So you have some kind of driving amplitude times a sine of some kind of driving frequency times t. Maybe you have another phase offset there. It doesn't really matter too much. What's going to happen is this force is going to be taking away the energy. The driving force is going to be giving energy back. And so what will end up happening is you'll have this initial part where this dies down, but then you'll start to have the driving force start to win out. And so whatever initial behavior the system would have had, it loses that energy, and it's the driving force that will end up being dominant in the long run. And that's going to win out over the initial behavior.
All right, so here I've got the same setup that we had last time. We've got our harmonic oscillator starting with a given position and velocity. We're graphing the energy. Notice that total energy is staying nice and constant. That's about to change. And we've got our glorious phase space plot showing us conservation of energy as well. Let's start by adding in the damping force here. So I've got this set to 0 right now. Let's set it equal to a small value, 0.01. So not a lot of damping, not a lot. And we'll leave the driving force turned off. So I'm just returning 0 here. So what I've done here is what I need to add is the damping force. So we'll add the damping. What is that a function of? I think it's the same thing, Tx and V. Yeah, okay. T, comma, X, comma, V. And we'll add driving. Well, let's add driving in a second when we actually want it. So now I've got my restoring force, my spring force, and my damping force. My damping force is set up in this nice simple setup of negative B times V. So the faster I go, the stronger the damping force is, and it's always going to point opposite of the velocity. It's always going to work to decrease the velocity. So again, the only thing I've added to the animation routine is just this one piece damping force. Everything else is the same. So let's see what impact this one thing has on our system. So I watch my oscillator here go back and forth. You notice it's not quite picking up as much speed as it did before. In fact, if I look at my velocity amplitude, I'm not quite getting as low as I did the last time. And then I'm not reaching quite the same height that I did. If I come down here to my energy graphs, they're still oscillating, right? Energy is still being exchanged between kinetic energy, potential energy. But if you look at these peaks that are traced out by the total energy, there's a little bit of a diagonal tilt to it, right? There's a little bit of energy loss as we go over that 10 seconds. My phase space plot is doing okay. It looks like there's a little bit of a disconnect right here. Let's do a couple things. First, let's have this go out a little bit farther in time. Let's have it go for 10 times as long. And let's make it go a little bit faster just so we can watch what happens a little bit better. Let's leave the damping force weak, though. We'll increase that in a little bit. So let's watch what happens here. So I'm going to put my cursor here as where the oscillator reached in the first cycle. Now let's see what happens to it when it gets back up here. Okay, it's doing all right. It's doing all right. Let's see, it goes up to the other side. Gonna come back around to the left. It looks like it's doing all right. I'm not losing too much, but you can kind of tell from here I'm losing a little bit. You notice that my peaks are getting shorter and my troughs are getting higher. So the amplitude itself is decreasing. Same thing with my velocity graph. And here I can definitely see it in the energy graph where I am steadily losing energy over the course of these oscillations, right? It's like this oscillation envelope is decreasing. In the phase space graph, I can definitely tell that something's going on because when this curve goes around on itself, it's falling inward. So it's spiraling inward. It's going very slowly, right? It's kind of painting out a path here, but it's definitely spiraling inward. So it's not able to get as far out in terms of position and velocity like it did before. Let's take a look at our, yeah, we can definitely tell then the position curve here. Oh, and I can even tell here, I think. Yeah, that's not quite getting as high as it did before. Let's see what happens if we make that damping force stronger. Let's make it stronger by a factor of 10. So go from 0.01 to 0.1. Press Control 2. All right, now let's watch how high this thing gets. All right, I made it up that high. I'll leave my cursor there. Let's see if it gets anywhere close to that like it did before. Oh, it didn't quite get to the edge of the cursor this time. So it's definitely more noticeable now. Yep, there it goes. It's lost almost a cursor length there. You can tell here I've got my peaks decaying, and here on the energy graph you can definitely see this decrease. And now instead of it being diagonal, you notice the total energy is going down in these steps, right? Because the thing is, the damping force can only take away energy when the thing is moving, right? It doesn't really do anything when the thing is stationary. And so these are only decreasing when my kinetic energy is on its way up, right? So the greater my kinetic energy is, the greater the decrease is. So that's why it kind of rests on top of the potential energy, because the damping force can't rob you of potential energy. It can only rob you of kinetic energy. And that's why you get this neat little step pattern here. Let's take a look at our phase space plot. This is where I love phase space, because here I can definitely tell that I'm losing something, right? Because I started out here, I'm spiraling around and around and around and around, but I'm falling inward each time. And so with each go around, with each cycle, I'm losing energy. So you can just imagine this thing, every time it goes from one ring to the next, it's losing energy as I go around this way. Now this system is what we call underdamping, where I'm able to still get out some oscillations. If I increase this damping coefficient enough, like let's say to a 1.0, I can eventually get to a point where the thing doesn't complete any cycles at all. All right, so like here, I'm still getting some oscillations out. The decay of the amplitude is definitely visible here, right? In fact, if you take each point at the peak here, so if I take this peak, the next peak, you actually get out an exponential curve. If you just ignore the rest, you get an exponential decay. Here we're definitely seeing the effects. We're losing a lot of energy at the beginning, and it's kind of leveling out. It's this nice, neat braided pattern here. Here you can definitely see we're spiraling inward, right? But eventually what I can do, if I make this high enough, let's try for 10. I can get it to where this thing doesn't complete any oscillations at all. It just slows down and goes down to the equilibrium point. So here you can see I exponentially decay down to the 0 mark, and I don't get any oscillations. You can see that in the energy too, my energy just gets sucked out by the damping force. And then here on the phase space plot, you can definitely tell it's different. It's not cycling around, right? Because these aren't oscillating. This thing is not cycling. So this thing goes from its initial point over here directly to 0, 0. So it's in the dead point right here. So you say, okay, well, how do we overcome this? Well, we add in the driving force. So here what we're going to do is comment this out, comment this in. So let's start with an amplitude of, let's say, 5 and a frequency of 1. Let's see what happens. Yeah, let's leave B up at 10. I'll probably decrease that in a second. So this has a different frequency than the original oscillator did. So let's see what happens. Now we've got the driving force. Let's not forget to add plus driving t comma x comma v. And we'll press Control 2. So here we're slowing down as we get to the edge here. I don't think that's going to be enough of a force to make this thing oscillate. You do see I get a little bit of wiggle here because it is being driven. So I'm getting this driving force here. So even though I've got this exponential decay here, I've still got the driving force. And eventually it's the driving force that wins. So I'm able to get the driving force results out here. Same thing here. I'm able to get the driving force. I don't have nearly the amplitude that I had before, right? I've only got the amplitude that I set up here, right? So I gave this an amplitude of 5. And I'm getting, well, I'm not getting amplitude 5, right? It's being modulated by, or affected by the damping force as well. Well, you notice I get here, I get some energy oscillations, right? And so I've got this initial behavior. The initial behavior eventually goes away and I just get the oscillatory behavior. Here, this is the interesting part to me as the phase space plot. I start out over here. Here is, so the trajectory this way is showing you what happens with the incredible damping force I've got. The wiggliness is showing me what happens with the driving force. And then finally here, I end up in this limit cycle where the driving force is taking over. So this is pretty much just the driving and damping force competing. I don't have any more initial effects there. This is where it's going to eventually end up. All right, let's look at a little bit happier system. Let's try decreasing this down to 0.1. Let's get a little bit better idea of what's going on with this. So here we've got our oscillations. So you have your oscillations like normal, right? This thing is oscillating up and down, but you've got these kinks in the middle, right? Those kinks are the result of the driving force because the driving force is trying to make this thing move with a different frequency than it naturally wants to go with. You can definitely see that in the velocity, right? I've got this overall sine wave, and then I've got the driving forces sine wave on top of that. And then our energy graph is a royal mess, right? Because the damping force is trying to rob me of energy. The driving force is trying to give me energy back. And so this is going to take a little while to settle out. Finally, you come down here to the phase space plot. This is where I love phase space plot. This is what you come to phase space to see, is this kind of great behavior. Do you see where it just looped back on itself there? That's so awesome. And so this is where you get this really interesting behavior. This is where you can get into what we call chaos, where the thing never repeats itself, or where it ends up tracing out every single point. Whether a system is or is not chaotic, is there's a lot of factors that determines that. But this is a really neat behavior here.